Oh, it didn't tell me it was recording. It normally says that. Okay, for the purposes of the recording, hello, I'm David. I'm coordinator of the Maths Learning Centre. This is a revision seminar for Introduction to Financial Maths. It's semester 1, 2021, and I've had some requests, and I'm going to talk about those things. So here we go. I'm just going to check if you mean what I think you mean. Are you talking about things like that sort of thing?
Yeah.
Yeah. Okay. All right. So quadratic. So this course has a section on functions and also annuities. And functions are a big idea in mathematics that turned up, oh gosh, about 100 years, 200 years ago, and became really useful. The general idea of a function is you sub something in and it spits something out. And the very simplest kinds of functions are linear functions. Whatever, that's linear. And it's linear when there's just a single x. You multiply it by a number, you add or subtract a number, and that's linear. And these produce straight lines, graphs. And then there are quadratic functions which look like this. And a quadratic function has anything with a square, has x squareds and possibly x's and possibly plain numbers, but it doesn't have to have all of those things. So you can also have just, 5x squared, that's okay. You can have something like this or plus 16 or whatever. And you can have all three pieces. And they don't have to be whole numbers either. It's tradition to play with the whole numbers, but you can just as easily have a half of x plus the square root of 3, and that's a perfectly good quadratic function. Any number okay, any number for the constant, any number for the numbers that are multiplied by the x's and the x squared, they're all fine. And these are the second simplest kind of graph, and the ones that have been are the most well known, that have lots of stuff known about them, so that you're allowed to just, like, the people who run these courses tend to assume that you just know what's going on with these things. So even though they teach them from scratch in this course, they sort of just assume you've seen it before. Okay. So all functions have various different properties, different places on the graph. It's possible for them to have x-intercepts and y-intercepts. That's pretty much it. They're definitely guaranteed to want to know about those things, but quadratic functions have other features as well. So all quadratic functions will have, I'm just going to draw some examples of what the graphs look like. They might look like this. It might look like that. Might look like that. They might be really flat like that. They might be sitting right on top of the, like just touching it like that, and all sorts of other things. And it could be that you can't even see them in the picture and they don't start till up here. Yeah. So quadratic functions, what they have in common is they're all this sort of shape. They're either like that or like that. And they're guaranteed to be that shape. And so they will have, sometimes they'll have x-intercepts on the graph. So this one has 2, this one has 2, this one doesn't have any, this one doesn't have any, this one doesn't have any, this one has 1. And they'll always have y-intercepts. This one has a y-intercept there. This one, the y-intercept won't happen until I extend the line and it's over here. This one, the y-intercept will happen over here. This one has a y-intercept here. This one has a y-intercept here. This one, it'll be over here. They always have y-intercepts because they're, yeah. And then quadratic functions, because they're all the same shape, will always have a turning point. And sorry, yep, and its official name is called the vertex. But there's an alternative name, which is a turning point. Because turning point is a generic word that is for any kind of function that has a hump like that. But for a quadratic function, we call it the vertex because reasons. It's also called a vertex because it's the only one. So I think that's the rule. If it only has one turning point, then you can call it a vertex. And quadratic functions only have one. All right. Cool. Sweet. And then what happens is that the way that the function is written can correspond to the way the graph looks. And we want to forge as close a connection as we can. All right. Cool. Just thinking. Right. Okay. So pretty much everything that you want to know about them can be organized in a great big table, and you can connect everything to it together. And writing your quadratic function in a different format will tell you different information about what the graph is like. If you ask a computer to plot every point, then like if you just type into Desmos, for example, y equals whatever, it'll just draw it for you. I don't know if you're allowed to use Desmos in your exam, but so that's that equation. And what Desmos is doing is it's pretty much using all the values of x and figuring out the matching value of y and drawing a dot. Yeah. Yeah.
Also, I have a question from where it's like if you use the equation, let's say you're writing form of y equals x plus bx plus c.
Cool. Excellent. I'm glad that that was in the tutorial because I want to talk about that. So there are several different formats that you can write a quadratic equation in. So forms to write the formula. There is this form. Something like that. This is called standard form. There is this form. These are not going to be the same one, I'm sorry. I'm just making up crap. Like that. That's the one that you just mentioned. And some people call this vertex form. And there is this form. Something like that. That's factorized form. And each form, in the USA, they would just call it factored form, not factorized. So each of these tells you, they all are able to, you can choose x's and calculate values of y. You can always sub x's into these formulas and it'll work just fine. But the way that they're written corresponds to things on the graph. So the factorized form is most useful for figuring out the x-intercepts. because the x-intercepts are there in the formula. So this one has x-intercepts. X-intercepts are x equals 6 and x equals minus 10.
Why isn't minus 10?
Yep, it's always the opposite. And it's because to get an x-intercept, you would need the y value to come out to 0. Because the x-axis, on the x-axis, all the y coordinates are 0. And to make this answer come out to 0, if x was 6, then I'd have 9 times 0 times something. And so that would be 0. And if x was minus 10 plus 10 is 0. And so that's why it's always the opposite of what number is next to it, so that they cancel out to make 0. Okay, lost my chat. All right, the vertex form will tell you what the vertex is. So this vertex, it will be the opposite of what's here next to the x, and it will be the same as what's here for the y.
You don't need any formula there?
Nope, it's right there in the formula if it's written in that format.
I also have a question from the student. We've given the vertex form, but it has to get the x values.
I'll get there. I'm just going to do all the things. But it's all good to mention these things so that I get to them. The standard form is not all that useful, but it does tell you what the y-intercept is. It's the constant term. So each of them is good for different purposes, and it's useful to be able to convert between them, but it's also useful to be able to know how to figure out the vertex from this one without actually turning it into vertex form. So it's good to be able to convert between them and to be able to figure it out from those things. So I'm going to talk about that. So no matter what form it's written in, the y-intercept is always calculated by substituting x equals 0 into the formula. And that is how you find the y-intercept of any function of any kind. And so as an example, if y was equal to 8, x plus 5 squared minus 7, the y-intercept would be y equals 8, 0 plus 5 squared minus 7. 8 times 25 would be 200. Always. And if you had it in factorized, the y-intercept would be 9 times 0 minus 6 times 0 plus 10, which would be 9 times minus 6 times 10, which would be, oh gosh, 9 times 6 would be 54, and we'd be minus 54, but times 10 would be minus 540. So y-intercept is always calculated that way, sub in the 0. But for a function that's already in standard form, when I sub in 0, this will be 0 and this will be 0, and so the y-intercept will be that number on the end. Yeah. So you're allowed to skip that bit because it always happens. But with these ones, you're going to have to sub it in because it's going to be a little hard to tell. That's y-intercepts. We do the vertex next. Okay. Crap, no, I'm not going to do the vertex next. Come back to that. The Xintercepts. Am I going to do that? No, not going to do that either. I'm going to do something else. I'm going to, I don't know if this is the official word, but I'm going to call it the orientation. So like which way up it is. So they either go this way or they go that way.
That's called minimum or maximum.
Yep, okay. So whether it has a minimum or a maximum. So this is completely controlled by the number that is attached to the x squared, which is called the leading coefficient. So this leading coefficient here is the one attached to the x squared. It's a positive number, which means this one will go up. And this is a positive number. Yep. 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 Yep, it'll have a minimum. So the idea is that whatever number attaches to the x squared, this is a positive number, which means that the orientation is concave up, which means it has a minimum, which is there at the bottom. Whereas if I had something that was like because this is a negative number, the orientation would be this way, which means it has a maximum, which is this point there. That's the maximum there. And it doesn't matter what format it's written with. If you can imagine which number is attached to the x squared, then it will do that same thing. So if I saw something like this, like that, if I expand this out, that -6 is going to get attached to the x squared when I expand it all out. And so this is negative, which means it's this way, which means it has a maximum. Because if I expanded this out, I get x squared and 7x and 5x and 35, and then the -6 would have to be times by all of those things. So we'll get times by the x squared eventually. So you don't have to even imagine that. You can just know that if it's constant times x plus something times x minus something, that being negative, that makes it same as this one being negative.
Yeah, can you like have a formula used for Vertex? I remember yours using.
Yep, not up to the vertex yet. I'm just figuring out whether the vertex is a top or a bottom. Okay, and it works just as well here. That's positive. And so therefore it's this way, and it has a minimum. So at the moment, this doesn't tell us whether it what the minimum is, it just tells us whether it has a minimum or not. And that's useful information because sometimes you can tell whether it meets the x-axis by depending on some things like that. Okay, next step is the x-intercepts. So I'll find the vertex later, but I just want to talk about the x-intercepts. So there are 6 options for the way it could be oriented. This is my x-axis. So 6 different pictures. Your function could be oriented upwards and miss the x-axis entirely. It could orient upwards and hit the x-axis once and come off again, or it could hit it twice. It could also do the same thing but up the other way. Whoa. Like that. So these ones have no x-intercepts. These ones have exactly 1 x-intercept. These ones have 2 x-intercepts. Which is different to lines. Straight lines always have exactly 1. Whereas quadratic functions can have 1 or 0, 0 or 1 or 2. And the question is, how do you tell which one of these situations you're in and how do you figure out what they are? Right. So the easiest one to tell is the factorized form. If it's in factorized form, then these are the x-intercepts. So if I saw something like this, then the x-intercepts are x equals -5 and x equals 3. It's always the opposite of what's here, because the x-intercepts make the y come out to 0. So if your function doesn't meet the x-axis, it's impossible to write it this way. Because if I could write it this way, it would meet the x-axis. So if it doesn't meet the x-axis, it's impossible to write this way. If it meets the x-axis exactly once, then both of these numbers will be the same number. And it'll actually be something like this. Like that. And so the x-intercept is just x equals 3, and that's the only answer. Technically, it's x equals 3 twice. Okay, so there's 2 here and there's only 1 here. How's everyone feeling? What about in the Zoom? All right, we're doing okay. So the quickest way to find x-intercepts, well, let me just step back a bit. So x-intercepts of any function of any kind happen when the y is equal to 0. And so for a function written in Vertex form, that's actually quite straightforward to do. And for a function written in factorized form, they're right there in the formula. But I just want to show you something, that the full version of the working usually goes. So it is okay to just straight up write them down from this point, but some people would write it like this. They'd go, to get the x-intercepts, solve y equals 0, and so we'll have x like that, because we've made the y equals 0. And then, well, 6 can't, the only way to multiply numbers together and get 0 is if one of them is 0. So either this is 0, which is not, or this is 0, or this is 0. Because you can't multiply numbers that aren't 0 together and get 0 as the answer. And so you can say, therefore, either x plus 5 is 0, or x minus 3 is 0, which means that x is minus 5, or x is equal to 3. That's the long version. You are allowed to just straight up go to the answer if it's in factorized form. Just pointing it out, but that's the long version. So you don't technically need this bit, but you can. But what if it was in this format? Something like that. In that case, it's not written in factorized form, so I don't know what the zeros are at the moment, but I can find the x-intercepts by solving y equals 0. Like that. And this only has one x in it. And so I can peel off the different things that have been done to x. So what's happened to x? It's been minus 5 and then squared and then times by 8 and then plus 32. I'll remove all of those pieces one at a time. Do a minus 32 to make that go away, which means it'll be here. Divide by 8. Oh crap, it's not going to be possible. Because at this point we've got a square number equals minus 4. And you can't have anything squared being a negative answer. And so there's no solutions. And so it has no x-intercepts. And that's a perfectly legitimate answer, to not have any. But if this had been a minus 32, then the y-intercept, sorry, damn it, x-intercepts then I would be adding 32 to both sides and then dividing by 8. Four, and then doing the square root. And it could be either plus 2 or minus 2. And then I could add 5 to both of those answers. So either x minus 5 is 2, which would make x equal to 7, or x minus 5 is minus 2, which would make x equal to 3. And that's our 2 answers. How are you feeling?
I'm a bit lost here.
Okay. Tell me more.
Previously, we just put in values in the x and just did the x in the set down.
So we're saying with this one you're okay with this working? Yeah. And now we're saying, well, what if it's not in factorized version? You can always see what happens if it's equal to 0. So to get the x-intercepts, you make the y equal to 0, put a 0 there, and I just wrote it the other way around. And then, since this equation's only got one x in it, I can progressively remove pieces of the numbers from the x. So I remove the 32, and then I divide it by the 8, and that gave me a minus 4. And then at this point, I can tell there's no solutions. Because to get rid of the squared, I would have to do a square root, and I can't do the square root of the negative 4. But if I had a different one where it was a minus in this spot instead of a plus, then I would do the same move. I would make it equal to 0. I could do a plus 32 to get rid of the minus 32. I could divide by the 8, that gets a 4. I can do the square root to get rid of the square, and the square root of 4 is 2. But it could have been a plus 2 or a minus 2. And then the options are either that x minus 5 is 2, or that x minus 5 is minus 2. And I add 5 to both parts here and I get 7. I add 5 to both parts here and I get 3. So this is a way of solving it if it's in this format. In fact, any format that only involves one x, you can always do that sort of thing.
What is this format called?
Sorry?
What is this format called?
Vertex form.
Factorization format.
Then it's already there. And if it's in this format, then I don't really have any hope. I have to convert it to one of the other formats. So if I'm very lucky, I can guess how to factorize it. But if I'm not, then there is a shortcut formula called the quadratic formula, which I'm sure is in this course. So I'm just going to put one here that so for example, this one, if I wanted to turn it into factorized form, then I would try and remove this number that's next to the x squared from all the bits. They've all got a 6 in them, so I'll divide by 6, like that. And then I would attempt to imagine, can I do this? Possibly with minuses. And if I expanded this out, I would get x times x, which would be x squared, that would produce this. X times whatever this number is, and this number times x, and together they would make the 5x, and this number times this number would make the 6. Yeah?
If x squared plus 5x minus 6, it can be factorized form, but it's plus 6. So
I think this one can be. So what would happen is that when I expand this out, this would go with this to make the x squared, this would go with this to make something involving an x, this would go with this to make something involving an x, and this would go with this to make a plain number, which is where the 6 came from. So I need to think of two things that add to give 5, and they have to multiply to give 6. So it could be 2 and 3, that'll do it. Okay. But I could have tried different numbers. I could have gone, well, 1 and 5 add to 5, but they multiply to give 5, so that's not right. 2 and sorry, 1 and 4 add to give 5, but they multiply to give 4. 2 and 3 add to give 5, and they times to give 6. That's the correct one. So it's 2 and 3. Well, the rules go that these two numbers added produces this number, and these two numbers multiplied produces this number. Yeah, so we were imagining things that add to 5. And trying to see what they multiply to see if I can make it match up with both ways. So 1 and 4 add to 5, but they multiply to give 4, so it's not coming out to the right answer. And 2 and 3 add to 5, and they multiply to give 6, so it's the correct answer. And it's really just trial and error. You just keep changing the numbers one at a time until you get one that works. So if you want to avoid doing that, there is a shortcut that will produce the correct numbers. And so just wait a second. The x-intercepts are x equals -2 and x equals -3 because it's always the opposite of what's here. Okay. If you want to avoid doing that, there's a magic formula called the quadratic formula, which says that if your function is written in this format, then the x-intercepts will be minus b plus or minus the square root of b squared minus 4ac all over 2a. And so if I had this one, y equals the one that I had before, I could go, okay, this is the number in position A, this is the number in position B, this is the number in position C. Then the x-intercepts will be x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. And I would have to figure out both options, the one with the plus and the one with the minus, and it would give me the answers. It's not going to be pretty. Oh, wow. Okay. They are both going to be negative. I can tell from here because if I do the minus minus, that'll be a negative answer. And 30 squared minus this is less than 30 squared. So when I square root it, it'll be less than 30. So I'll get minus 30 plus something less than 30, which is negative. So, yeah. But I would need to be very careful to put the brackets in the right place so that the line there doesn't cause problems. In a calculator, I mean, if your calculator does fractions, then that's fine. If your calculator doesn't, then you'll have to type, you know, minus 30 plus the square root of and then brackets there and divided by 2 times 6. Sorry? Yeah. One of them will be -3 and the other one will be -2 because we knew that already because we already solved this problem. But you don't always know that. I would recommend that if they do have a 6 in all of them to factorize that out first and then just do the quadratic formula on the bit left because the numbers will be smaller. So what this is telling me is that if it's already in vertex form, then I can solve it like this. If it's already in factorized form, then the answers are there on the page. And if it's in standard form, then you can attempt to turn it into factorized form, or you can use the quadratic formula. And the quadratic formula will always work. Okay. And then the last thing to do is where the vertex is. But before I do that, I wanted to show you how to convert from standard to... no, I won't. I'll tell you where the vertex is. So it's in vertex form. The vertex is right there in the formula. It'll be the opposite of what's next to the x and the same as the constant term. And that's literally it. And that's because it starts at 9 and then you add on this square thing. So the further away you get from 5, the higher the answer is going to get. And so 5 is the bottom. Because the smallest answer this can possibly be will happen when this is 0. That's why that's the vertex. Cool. And if it's in standard form, then the vertex, you can find the x-coordinate of the vertex pretty straightforwardly. It will be this number divided by 2 of that number. So I'm just going to do the formula. If it's ax squared plus bx plus c, the vertex x-coordinate will be minus b over 2a, which is this bit of the quadratic formula. And so for this formula, for this one, the vertex x-coordinate will be at x equals minus 15 over 2 times 9, whatever that is. And 3 goes into both of those, so I could factorize it down, but it's not very good. And if I wanted to figure out the y-coordinate of the vertex, I would have to sub this into the formula to see what the y came out to be. Which would be a horrible fraction with a very large numerator. Something over 36. I don't know what it is. Okay. All right, and what if it's in factorized form already? For example. So I know what the x-intercepts are. The vertex x-intercept is always halfway between the two x-intercepts. So there's 3 and there's 8 and this distance is 5. So we'll have to go 2.5 up from the 3, so 5.5. So it'll be the average of those two numbers. So you'll get x equals the average of those two. Or you could leave it as a fraction if you wanted. And then to get the y-coordinate, you have to sub that into the formula, same as you did for the other one. But that's just something I wanted to point it out, that the vertex is always halfway between the 2 zeros if there's 2 zeros. Like if there's 2 x-intercepts, the vertex is halfway between. So you don't have to do the minus b over 2. You don't have to expand it out and then get the minus b over 2a. You just go halfway between these. Yeah. And the only other thing is how to convert between these. I've already shown you how to convert from standard to factorized, which doesn't always work, but it's if you're lucky, you can do it. To convert from factorized to standard, you expand it out. And to convert from vertex to standard, you expand it out. The tricky bit is converting to standard to vertex. And this process is called completing the square. And it can be quite complicated. Did they use this phrase in this course? So if you ever want to know how it's done, now you know what to Google. So that particular exercise was probably doing it by the one that you're talking about, avoiding some of the details. Yeah. But you know, if one way is you can complete the square, But the other way is to find the vertex, and then you know what the vertex form is going to be. Because, for example, so completing the square is the process, and I'm not going to show you because they didn't, but I can talk about it another time. But you can I'm not going to use that one if that's okay. I'm going to use a different one. All right, this is my function. I can find the vertex, which will be at minus b over 2a, which is at 30 over 6, which is 5. That's what the x-coordinate of the vertex is. The y-coordinate will be what I get when I put 5 into the formula. And so this will be 3 times 25 minus, what's 30 times 5? That'd be 150, wouldn't it? 3 lots of 25 would be 75. So we got minus 75 plus 10 would be minus 65, plus another 5 would be minus 60, plus 2 would be minus 58. Oh, these two together, that's plus 75, minus 150 is minus 75. I'm pretty sure I'm right. That's what calculators are for. And so that means that in vertex form is guaranteed to be an x minus 5 and a minus 58 on the end, because that's how the vertex form works. The x-coordinate of the vertex goes here, and the y-coordinate of the vertex goes here. And this number will be the same as this number. Yay! That's probably the quickest way to convert to vertex form. You can learn the process of completing the square, and that'll work fine as well. But that's the quickest way.
What did you say was from vertex to standard form?
Expand it out. So if I wanted to go back to standard form just to make sure I was right, then that x squared, x minus 5 all squared would be x squared minus 2 times 5 and then plus 5 squared. That's how to expand out a square. And then I'll have 3x squared minus 30x plus 75 minus 58 and 3x squared. So minus 60 would have been 15, but I haven't taken off 60, I've only taken off 2, so yeah, it works out. So that was expanding it out. And so I was correct, this really is the same as that. I wouldn't always do that bit of working unless I had lots of time. Yeah. Cool, so that's sort of everything I know about quadratic functions. How are we feeling? It's this squared, and at the other end there's this squared, and in the middle there's 2 times this, and the 2 times the 5 causes the 10. Yeah. So the x plus number squared is x squared and a squared and 2 times a times x. And if it's a minus, then this is a minus. And since it was a 5, I got 2 times 5, which is what made the 10. All right. We've done extremely well. I'm just going to put all these in order. Yes, that's what I was putting in order. Okay. All right, let's talk about these other things. Right. What's your name? Yoshki has asked about determinants, and he has a specific example actually, so we're going to run with that. So the first thing I want to say just before I work with your problem is that determinants are a thing that you do to square matrices and they produce a number. So you've got a square matrix. It can be 3 by 3 or 4 by 4 or 2 by 2 or whatever. And when you do the determinant, you get a single number calculated from all of these. And the process of calculating that can be quite complicated if it's a big matrix. The people who are listening online, are you comfortable with calculating determinants? No, I assume we're okay. All right. So determinants are a thing you can do to square matrices. And anytime you learn a new operation that you're allowed to perform, you need to see how it interacts with other things that you know how to do. So stuff that you can do to matrices is you can add them and you can multiply them. You can find the inverse. Did they cover transposes in this course? Yeah. You can do powers, like squared, and you can do transpose. These are all things you can do to matrices. And we know we can do them to matrices. And our question is, now that we can do determinants, how do they interact? Oh, we can multiply them by constants as well. Yeah? Okay. And in fact, there's one more thing, and you can do row operations on matrices as well. And that's, I don't know if they've taught you how row operations interact with determinants. So it's a process that takes your matrix and produces a single number. And you combine all these numbers together with pluses and minuses and multiplying and stuff, and it produces this answer. So the long version is that for a single number, the determinant of a matrix with one number in it is that number. And then for a 2 by 2 matrix, just so you can see what's going on here, you pick any row or column, you go along the top row, and you have 3 and minus 5, and then the 3 will be multiplied by its opposite corner, and the 5 will be multiplied by its opposite corner. Because that's the rules. When they invented determinants in the 1820s, that's just, they figured it out that this is the best plan. Yeah. Piece of trivia for you. So Lewis Carroll, who wrote Alice in Wonderland, he was a mathematician and his research area was determinants back in the 1860s. Feel like this is the best plan to create a calculation that will tell you if your matrix is invertible or not, basically. All right. And so you could have done this the other way. You could have come down this one and gone 3 and minus 7. So I could have gone 3 in the top corner, minus 7 here, and multiplied this one by its opposite and this one by its opposite, and it would have come to the same answer. So it doesn't really matter. And most people don't think of it that way. They think of it as the downwards diagonal minus the upwards diagonal. Yeah. So this will be -2, which is just an answer. It's not particularly, we don't really know what to do with that. It's just a number that it produces. Okay, the only time when a determinant really tells you something extremely useful is when it comes out to 0. Though in physics, they use the actual size of this determinant to mean something. It tells you the area of some sort of shape. So, yeah. Okay, so for 3 by 3 matrices, and for anything higher, you build it out of smaller numbers. So it doesn't matter which row or column you pick, but most people pick the first row, and you have 3 and -2 and +1. So you always alternate between plus and minus and plus. So see here, this one I had plus and minus. This one's gonna be 3 by 3, it's gonna be plus minus plus. And then the thing you multiply by the 3 by is whatever this determinant is. And the thing you multiply the -2 by is whatever determinant you get by removing the spot, the position that the 2 is in. And whatever you multiply this 1 by is whatever you get by removing the position that the 1 is in. Damn it.
I don't know which topic.
That's what we know.
And whatever that works out to be is the determinant. And if you had a 4 by 4 matrix, you would go on the top row and you have plus minus, and then each of them would be multiplied by a 3 by 3 determinant, and that 3 by 3 determinant would have to be figured out like this, where you go plus minus plus, and that's how it goes. You can use the column, and it will work.
So we're trying to get 1. You have to do the ones that's not under the 1.
Yep, that's right. You have to use this. Yep, you have to use this. The number that you put in this spot, the place where it came from, you have to cross that row and column out. Yep, exactly. And you are actually allowed to use any row or column to start with. You just have to keep track of whether it starts at plus or starts at minus. So I could also have used instead this row. So as an alternative, I could have said that the determinant of this matrix, I could have said, let me just track this here. The top left corner is a plus. That one would be a minus because I switched one position. It would be -8 times a determinant, plus 0 times a determinant, -6 times a determinant. And these determinants would be the ones you get by crossing out the position that you're in. So this one would be 2, 1, 1, 5. This one would be 3, 1, 1, 5. And this one would be 3, 2, 1, 1. And this one I don't need to find because it's 0 times that anyway. So what most people do when they calculate this is they try and pick the row or column that's got the most zeros in it, because it means you get the least amount of work at the end. So that's what determinants are. In order to answer your problem, we need to know how determinants interact with other things. So the determinant of A plus B, there's no rule for that. Determinant does not play well with addition. So just don't try. The determinant of A times B is the same as the determinant of A times the determinant of B. The determinant, and that means that if we've got the determinant of A squared, that's the same as the determinant of A times the determinant of A, by using that same rule. And this works for any power. If it was A to the 5, we'd have determinant of A to the power of 5. The determinant of A transpose is the same as the determinant of A. Because it doesn't matter whether you do it by rows or columns, switching the rows and the columns isn't going to make a difference. And so this move of transpose is switching the rows to columns. The transpose turns the rows into columns and the columns into rows. And so if I did the transpose, if this was A, then A transpose would take this first row and write it as a column, and this second row and write it as a column, and this third row and write it as a column. You could also do it by the columns and turn them into rows, and it would work just as well. And so because determinants, it doesn't matter whether you use the rows or the columns first, same answer either way. The row operations, if you have a matrix A and it has this determinant, and you do, any row becomes some multiple of that row, then that will multiply the determinant by 3. If I multiply by 8, that would multiply the determinant by 8. And it doesn't matter which row it is. If you just do one row and multiply it by that number, it'll multiply the determinant by that number. That's the most important one. But the other one is that if you take a row and you add on some multiple of another row, the determinant will stay exactly the same. It won't change at all. Yep. And if you do the row swap, where you swap two rows, the determinant will be minus what it was before. Yep. If it was already negative, it would become positive.
What if it's like row 1 plus another?
Won't make any difference. If you have, you can't just add 5 to a row. That's not a row operation you're allowed to do. But if you have row 1 is row 1 plus or minus any multiple of any other row, it won't make a difference to the determinant at all. Okay, so this one, if A has 3 rows, or if A has 4 rows, let me do that, then I'd be multiplying the first row by 3, which would multiply the determinant by 3. And I'd be multiplying the second row by 3 as well, because I've multiplied the whole matrix by 3. And I'd multiply the third row by 3 and the fourth row by 3. So I would end up multiplying by 3 however many times it has rows. So this, the determinant of multiple of A is where this is how many rows there are. And then finally, the determinant of the inverse is 1 over the determinant. All right, these are the rules for how determinants behave. How are people feeling about this list?
I'm just not feeling good.
This one here?
Yeah.
So this rule says that if you times one row by a number, you times the determinant by that number. 3A means you've times all the rows by 3. So you have to times it by 3 once for each row. I'll do a proper example in a second. Well, it'll be 3 times bigger for the first row, and then 3 times bigger again for the second row, and then 3 times bigger again for the third row, and then 3 times bigger again for the however many rows it has. So this one you can only decide based on how many rows the matrix actually has. So I'm just going to show you something. This matrix here, the determinant of A is 5 times minus 1 minus 6 times 9. Because that's how you do it. This one minus this one. And so I've got minus 5 minus 54. So I get 59, minus 59, which is a horrible number. What happens if I do 2A? That'll be 10 and 60 and 90 and minus 10. And so I'll get 50. Sorry, why did I get a 10? I'm doing, oh, damn it. I'm going to do 10A. So that's what I actually did. 10A. And so this will be 50 times minus 10 minus 60 times 90. And these are the same answers I had before, but it's now 500 and not 5. And it's not 54, it's 5400. And so I'll get this. So multiplying the matrix by 10 ended up multiplying the determinant by 100. And that's because this one is get times by 10 and this one gets times by 10 as well. And they're going to be multiplied by each other. And so every time you multiply one row by a number, it times it by that. So I could have done this. The determinant of 10A should be the determinant of A times 10 for the first row and times 10 for the second row. Yeah. So that's how it works. And if it was a 3 by 3 matrix, I would have to times by 10 3 times. Yes, let me write down the problem now. Yes, I'm very excited. So the problem on the board is, suppose A is a 4 by 4 matrix with the determinant of A is 5. Then what is the determinant of 2A inverse? Okay. What were you going to do?
Like 2 power 4.
Exactly.
It's 16.
Yep.
Then 16 times 5 is 80. So 80 power minus 1. So 1 over 80.
Right, very close. So you're doing very well doing that in your head. I would need to write it down. So just to make it absolutely clear, whatever the determinant of A inverse is, multiplying by 2 will end up multiplying it by 2 4 times, once for each row that it has, because it's a 4 by 4 matrix, which is the same as. So some people remember the rule this way and they go straight to this, which is what you did. Okay, so that's 16 times the determinant of A inverse. And the determinant of A inverse all by itself, that is times 1 over det A. And so I'll get 16 times 1/5, which is 16 over 5.
Yeah, I did that 16 times 5.
Yeah, and then to the inverse, yeah. Yeah. I'm pretty sure I've got this right. I'm going to try it a different way and see if I get the same answer. No, I can't think of another way of doing this, actually. Yeah, because I have to remove the 2 first because the inverse is better. Worth pointing out that I know it actually has an inverse because most matrices don't have one. But since the determinant isn't 0, that means the inverse does actually in fact exist. And so it's okay to find its determinant. Yeah. How you doing with that? I got a new person a while ago. Hello, Aaron. And so all of those rules are designed to, like, it's just a standard thing to do in maths. If you know stuff you can do, you figure out how it relates to all the other things that you know how to do. And it's a useful thing for yourself if you're creating a nice little sheet for yourself to look at in the exam, is to go, well, let's write down everything I know how to do the matrices and how does it interact with determinants. Yeah. Okay. Now we are up to these deferred annuities. Is it 2 R's or is it 2 F? 2 R's. Okay, so what does deferred annuity mean? Does it mean that the payments don't start for a while? So I'm just going to imagine in my head it's like this is time. So an ordinary annuity, the interest comes on at, like the payment happens at the end of the period. Is that right?
At the end of the month and the quarter and the year.
Yeah.
And you deduce.
Okay. Weird. Due would seem to me have the opposite meaning, but whatever. I'm just going to have to remember it. So is that what deferred means, that the payments don't start for a while? Like this is the end of the first periods.
Yes, and I haven't watched that lecture.
So maybe the payments start here. Do they call it R normally, the regular payment? I think that's my idea. Have you found it? I'd have to look this one up because it's a terminology thing, so. Do any of you who are in the Zoom have access to the notes that they could share on the screen if I asked you to? Right.
You feel free to skip a bit.
Yeah. Okay. Just give me a second to look at this example. Okay. Did you have an actual problem that you were wanting to work on? Always have to look this stuff up.
Question one, maybe.
So an annuity pays $200 each month for 3 years at 7% per annum, compounded monthly. And then we want the present value if, so this is an annuity versus an annuity due, right?
Yeah.
Okay. So this one isn't a deferred annuity as far as I know. this is, well, but that's okay. I'm still going to do it because we need to do it anyway. So I'm just going to cross that out. Okay, let's just do this problem and see how we go. So in my head in part A, we have 3 years, and this is now. And the 3 years would be worth 12, would be worth 36 months, right? And so there's a lot more of these than I've drawn. Yep. So 1, 2, 3, and then however many there are. Okay. And so in the first one, the payments begin here at the end of each month, and there's one at the end of the 36 months. Okay. So if I've got this right, I always get the formulas for this wrong, but I'm just going to thinking it out. You're saying the percent compounded monthly. So you're saying 7% monthly is 7/12. 7% per annum monthly is 7% per month, right? So what did you say, 0.58? Okay. And so things that are 1 month in the future have to be discounted by 1 point. And so that would be 0.0. Is that right? In terms of as a decimal? So the one that's 1 month into the future will be worth this much as a present value, this one here. And the one that's 2 months into the future will be this present value. And so on all the way to this one.
So I need to calculate 36.
Sorry? I mean, you don't have to calculate this. There is a formula for this. But this is what it would be if you were just doing it by hand. Yeah, there is a formula for it, and I always forget what the formula is, and I would have to look it up. And it is here, actually, wasn't it? So it says here that the present value would be made of the regular payment. So this is the formula that I've got from the notes here. Regular payment, 1 minus 1 plus I to the negative n over I, where I is the decimal version of the per period interest rate. And so the present value will be the regular payment, 1 minus 1.0058 to the minus 36 over 0.0058.
Why it's minus 36?
It's to do with the fact that all of these are, see how these are all on the bottom of the fraction? That's all to the power of negative powers. And when you add them all up, that's where this negative power came from. I can do the arithmetic sums, the geometric sum thing to get it. I'm just going to check if I've got the, you don't have to do this to do the working, but I'm just going to check if I'm doing this right. Oh, bless you. Bless you. Like that. And then this is, all of these have a 1 over 1.0058. I could be doing that wrong. I always, yeah. So I know how geometric sums work. to the 35. And that's the same as got 1, I've got to the -1, all the way up to 1.0058 to the -35. And that is don't do this often enough to be able to just do it quickly, I'm sorry. I'm just going to put a few more of them in. And that I know how to add up. That's a geometric series. And the geometric series, the answer is the thing that's being multiplied over and over to the power of 1 more than this. One minus that thing. Over 1 minus that thing. And I've done something wrong. Always get this wrong. Yeah, no, I just wanted to see where the formula came from. So that's where it comes from. That's where the minus is, because there's a -1 to the power of 36. But I've done something wrong. No, always get it wrong. Yeah. So this is the formula, and it works out to this. And I'll just put it in a calculator. Can't use your phone in the exam for your calculator.
No, we're going to use a calculator on the laptop.
And of course you can't see that at all. It's too bright. Is this what the answer worked out to be for part A?
6,481.13.
Awesome.
I'll just plug it in formula.
Yeah.
Payments. And then just call present day.
Yeah. So I just want to check something. Okay, cool. All right. Have they used sum notation in this course? No? No, that's all right. That's okay. I was just checking if my instinct was right about how to do it. So I've done the sum of 200 divided by 1.0058 to the power of something, which is what I was writing on the page earlier, and it comes with the same answer, so that's good. Okay, but the formula is the right formula. Okay, so that's that. But if it's part B, then everything is happening earlier, right? So part B was the present value if it's at the beginning of each month, which is an annuity due. So now the payments happen here instead. Yeah, you take that or I'll forget it. So with an annuity due, everything is worth a little bit more because it happens sooner. Because present values that are closer to you are worth more. So my instinct, there's probably a formula for it, but my instinct is that it would multiply this by 1.0058. And that would give me the answer. Because everything's earlier. So we've got a 200 now, so that's worth 200. And then a 200 1 month into the future. And then one that's 2 months into the future. And then one that's 35 months into the future, because we don't go all the way to 36 because it's the beginning of the last month. And then these are the same as these, except these ones all have another 1.058 on the bottom. And so I reckon it should be that the present value is the old present value from my ordinary annuity, which was 6481, times 1.0058. Because they're all that much earlier, so they're all worth that much extra. Is that how he did it?
So you're looking for the present value of each cash flow or like the whole thing? You'll
need a present value of one of them and a present value of the other, and then you're supposed to compare them to decide which one's more. Yeah, I was right. Yeah, I'm all good. Yep, that's exactly the formula I thought it would be.
Well, what do you say that is 200 plus 200 and minus 2?
Oh, I haven't used the formula. I've taken the other formula and times it by this, because everything's 1 month earlier.
Yeah.
So that's how I would do it. I don't know if that's what the lecturer would hope for, but I could do an ordinary annuity and then shift everything closer in time by 1 month, which is timesing by this. Because we would undiscount it all by a month, which is multiplying it by this. That's how I would do it. How are people feeling about that?
So that's a annuity like discount.
Yeah. So you don't need this to do the working. I was just imagining the discounting of every 200.
Just this formula here like gets me to like, why is it so complicated while that's just so simple? You know what I mean?
Yep, I know the formula you're looking at. Okay, now let's do a deferred annuity. What if we have 600 a quarter at just give me a minute, at 8% per annum, compounded quarterly. And we're going to have 20 payments, but they don't start until the beginning of don't start until the end of like 2 years, and still 2 years time. This is called a deferred annuity because it's still an annuity, but it doesn't happen until later, which is what the word deferred means. So the story is that here's now, and then we've got 1 quarter, 2 quarter, 1, 2, 3, 4 quarters. That's the first year, and then that's so 1, 2, 3, 4. That's the first year. That's the second year, And this is when the payments start. And then there's 20 payments. Yeah, each quarter. Sorry? Yeah, for 5 years. So there's a payment here, payment here, there's payment here, there's payment here. Yep. And they don't start till here. Okay. So if it started at the end of the next quarter, so if it was this instead, and the payments were right away, that would be an ordinary annuity. Okay? And so if we start at the end of first quarter, then the present value would be the regular payment times 1 minus plus I to the minus n over I. That's what it would have been if it had started, if it had been an ordinary annuity starting now. And so that would have been 600, 1 minus, oh crap, 8% per annum compounded quarterly is 2% per quarter. Yeah. So that's 8% divided by 4 is 2%. So it'll be 1.02 to the minus 20 over 0.02. That's what it would be. Okay, that's what the present value would be if we started now. But this one doesn't start until how many quarters into the future onto that? 1, 2, 3, 4, 5, 6, 7 quarters further into the future. No, because it starts at exactly 2 years' time from now. All right. So it's been deferred 7 periods from the ordinary one. So if we start, yeah.
Is it 20 payments total or 20 payments after 2 years?
20 payments total once you start payments. So what I mean is these payments here, there's 20 of them.
Oh, so after 2 years, it's 20 payments.
Yeah. You don't get any payments for the first 2 years. So if we start at the end of the 7th quarter, which is what happens, which is 2 years' time, because the end of the 7th, no, it would be the end of the 8th quarter, wouldn't it?
We start at the 8th quarter, the end of the 7th quarter.
Yeah, start at the end of the 8th quarter, which is 7 quarters into the future compared to this one, because this one started at the end of the 1st quarter. 7 quarters into the future. Because that's the difference between these. This one was the end of the 1st quarter, this one's the end of the 8th quarter. 7 quarters difference. Cool. Then everything will have to be discounted 7 quarters into the future. So I'll take the original one I had, which was this. And I'll have to discount it, which usually means dividing by the interest rate thingy. Which is the same as multiplying by 1.02 to the negative 7, which is the formula that you had here, Luca. It has a negative k in it. Ah, crap. Has a negative k. That's because we're dividing by it, because we're discounting.
Or we can just times the 1 plus 0.2 negative 7.
Yeah. So that would have worked as well.
Yeah.
I have trouble processing that without thinking of it as a division, but I could have gone like that. Because this one here is what discounts it, because everything's further into the future. So the whole payment, the entire annuity, is 7 quarters into the future, so I'm going to have to discount it by 1.02 to the power of 7. Yeah, and it's a negative because I'm discounting.
And when we get that result, what does that actually tell us? It tells us the present value
Of the deferred annuity.
the deferred annuity, like of all the cash flows.
Yep, all of that cash flow, taking into account that it doesn't start until the end of 2 years.
Yeah.
And so something that doesn't start until the future has a lower present value because money in the future is worth less. Because if you're going to buy an annuity, you'd prefer it to start now, right?
Mm-hmm.
And so the present value is trying to take that into account, trying to say that.
Remember the last example you did?
Mm-hmm.
One annuity, and then after what was it, you tried to do in June.
Yeah.
New time went by just to write.
Yep.
I thought like the present value was higher than the actual ordinary.
So the present value of an annuity due should be higher than the same thing for an annuity, ordinary annuity, because everything is being paid one period earlier, and so it's worth more.
That's the combined present value of all the cash flows is higher when it's due than rather than.
Correct. As long as there's the same number of payments.
Yeah.
Yeah.
Well, in this case, it's the number of payments.
Yeah.
So we got a little
How are we feeling? Yes. Feel free. You have your phone back. Okay. Thank you very much for coming. Don't forget the Maths Learning Centre is open both face-to-face and online every weekday until the end of the exam period. I personally won't be there tomorrow because I'll be doing revision seminars, but I'll be there. I'll be in the Zoom all day on Friday. Let me see if let me organise them. I'm just going to stop the recording. Thanks very much, everybody.